Hey, Mr. Pham, I got a question.
Yeah, go ahead.
The lady that said her test two failed, did she test her program against somebody else's hardware?
You mean the test number 2 failed?
You know how, Mr. Pham, you always are telling us about troubleshooting techniques.
Yeah.
So what I was saying was, did she test her program against somebody else's hardware and her hardware against somebody else's program?
Oh no, it was at the end of the night, and I was really super tired, and
Okay, I forget, what's your name again?
Lisa.
Lisa, yeah, Lisa.
Hi, Joseph.
Yeah, hi. What Mr. Pham normally have us do is say like you have D-Lab 1 or D-Lab 2
Mm,
and the D-Lab fails.
mm,
Okay, you need to test your program and you need to test the hardware. You test your hardware against somebody else's program and their program against your hardware. But you cross do it.
uh-huh.
You understand what I'm saying, Mr.
Yeah,
Pham?
yeah, that's a good troubleshooting idea there. That's not a bad idea. I did pass test 1. So
Yeah, but how,
you know, so
okay, one of the things is like if you having problems with your D-Lab, you can't use your own D-Lab to test your own D-Lab. You can say like if Mr. Pham wrote the program, then you could do put your hardware and his program together and see if it worked.
right. Okay, that makes good sense.
Is that right, Mr. Pham?
Just a minute.
Oh, you know.
Okay. Repeat it.
That's one person's program against another person's hardware as a troubleshooting technique.
Okay. Now, I can tell you, only one unknown, you can solve the problem. If you get 2 unknown, no way. Let's bring it up to you to understand when you run the test fail, all right?
Yes.
Either your program is not right, or your circuit board build not right.
Right.
2 unknown, you cannot solve the problem.
So what I was saying, Mr. Pham, when you have that situation, you get another person's hardware and test your program against their hardware and vice versa.
Well,
Yeah,
I would first test my board, and see if
either one.
yeah.
If someone get the board, the same thing, it's working already. You can run your program to test on that. If it pass, that means your software get a okay. Now you know your hardware got a problem. Just one by one.
Right.
Okay. The thing is later, I get the program execution. That means you cannot see the code. Let for your guy, after you build your circuit, you run my test. If it pass, your circuitry working, then now you can using your software. If it's not working, problem is your software. However, we try Monday, we'll get that lab done. Not be done. Okay? We
Yep.
have to speed it up. Okay, today we're talking about set, reset, latch, NOR gate. First thing you see on this circuitry here, input R, input S, output Q, output not Q. That only telling you one thing. If Q 0 equals 0, then not Q will be 1. And not Q equal 0, then Q have to be 1. They have to be opposite all the time. Okay? So now, this is just a logic gate. We'll see. If you get input A and B here, the output here will be, first thing, forget about the bubble. Forget about that one. Then you get an OR gate, right?
Mhm.
Right.
Without the bubble. OR gate, that means A or B. Okay? A or B. OR gate. And when you get an inverter not here, you put a bar over. Now you're converting the sum into the product, so you can get not A, or will be N, not B. That's easy for you. In order to talking about the output, if you get 0 here, 1 here, what output?
Zero.
If you get A0, B1, what output Q?
Oh, Q1.
Come on.
Oh,
That's what I given to you. The formula right here. Okay, A0, B1. A0 not A will be 1. B equal 1 not B will be 0. 1 and 0. You must get 0. When I see the NOR gate, they given the input, I cannot tell him what output supposed to be. I have to get until I get this formula. Not A and not B. Then I can tell you what output supposed to be. Okay? And now you get another one. This is NAND gate. We already get through. I going back without the bubble. They will be N. Okay? If you get A here, B here. So, first thing, you get A and B. And now you get a inverted bubble. Put the bar over. You get a product, you convert into the sum. So you can get not A. And now will be R, not B. So if you get a 0 here, one here. What give?
One.
I know Q will be equal not A or not B. A 0, not A will be 1. 1 you all with anything, they must be 1. That is the NOR gate working. If you don't know how it's working, you cannot analyze it. Okay, so what they say, active high input at a lot. Just the name. Active low. Okay. Only thing is, if you get input, okay, either 0 or 1, you're able to calculate the Q. Okay. And now, this is the symbol here. The symbol here. They're telling you this circuitry will be inside. You get S and R. Okay? I given you the example. If you get a 0 here, 0 here, what Q equal? That means you get a 0 here, 0 here. Okay? We already know that NOR gate. Okay? Again, A, B, you see that? Even I couldn't remember. If you get AB, then AB, A or B, not A, not B. Okay? Or not F and not R. So A0, then that will be not 1. R0. So basically you get a 1. So Q will be equal to 1. Now, Q equal to 1. Going back here. You see that? They fit it back here. So 1 and 0. Okay? 1 and 0, they're telling you Q, not Q. 0. Okay? And now, if not Q 0, they go back here. You get 0 here. Okay? So, basically, for at R, okay, latch, you can get the input at are either 0, 0, 0, 1, 1, 0, 1, 1. And you can calculate the output. Same thing for that guy. You can see the difference. Either SR, okay, on this part here or on this part here. They get two input S and R. Output Q, not Q. Same thing on that one. You get input S, input R, output Q and not Q. My question is, if you're looking into symbol, what the difference? Can you say what the difference?
Negative R and S.
You see on that part here and this part here, they get the same S input, R input, Q and not Q out. What is the difference? Who can recognize?
Not S is,
You can see right here.
yes, the bubble.
Okay. Now,
The input on the second one, both of them, the S and the R is low. The input on the first one is high. So that's why it's active high. And on the
Perfect.
first,
active high.
right. And the one with the
Active
bubble on
low.
the second one is active low.
That means 0, okay, will be set now. What that mean? When they say set, okay, and R mean reset. When we say set, that means Q equal 1.
Reset 0.
Right. If you know Q, you know not Q. Normally, they have to be opposite. This is the truth table. Okay, you don't have to analyze. However, this is a truth table telling you for input SR what Q and not Q. Now, if you're looking on the first one here, I'm talking about that one. This is the truth table. Try to explain to you. First thing 0, 0. If you're looking at 0, 0 input and you're looking at the output, Q and not Q. This
Oh,
is
set and
Q.
reset can't be 0 at the same time.
Yeah, this is a not Q. They said not allowed. Okay. Now we try to say what that means, not allowed. If you get a 0 here, what Q? Can you tell me?
If you get a 0 where?
Input 0 here. Right here. What kill? You know that is a name. That means not A or not B.
0.
1 0. Doesn't matter what the input here. Doesn't matter. Kill must be 1. Again,
One.
I'm telling you again. If you get AB, so for the AND gate, A and B, and you put the inverter, the bar over. You get not A, and will be R, not B. So S equals 0, 0 not be 1. So you adding anything, they have to be 1. Okay? So if R 0, then not Q also be 1. Again,
Not allowed.
Q, yeah, Q and not Q must be opposite. Q1, not Q must be 0. Q0, not Q must be 1. They cannot be the same. That's why they're telling you, not allowed. That means you cannot apply both to 0. You understand that not allowed.
You're not allowed to put 2 zeros on the input like S and R. Is that right?
Correct. Never happened. What the hell? Okay, that means not allowed. And if you get S0 R1, then Q1, not Q0. And if you get S equal 1, R0, Q equal 0, not Q1. Okay? When you get S1, R1, output will be no change. No change, that means if it was 0, they still be 0. If it was 1 and they still be 1, that means no change. So when you're looking into the logic circuitry here, and you get a truth table here, what I want to make sure, if we get an input S and R, you're able to tell me what Q equal and not Q equal by looking into truth table. And that apply the same for the NOR gate here. Okay, same thing. Okay, when they be no change, or when they be not allowed, or when Q0 not Q1, Q1 not Q0. You will need that. Okay, you don't have to memorize, but when you're looking into the table, you can telling me what's output. Okay, now we see on that one. You understand if the S and R waveform, this is the waveform. Now waveform that means this is logic 1. Okay. 1, 0, 1, 0, 1, 0, 1, 0, 1. That's what they call waveform. Computer cannot understand the 1 or 0. No, no way. They're working with the 1 and 0. However, you cannot send directly 1 or 0 to the computer. So that's why they need the waveform. The computer looking into this waveform, they can converting back to 1 or 0. Okay? So this is a S and this is a R. 1, 0, 1. Okay, now what they want. Okay, that are waveform. Insert below, apply to the input of the last S in SO. Determine the waveform that will be observed on the Q output. Assume that Q initially low. So basically, we start raw Q. That will be Q here. At the beginning, they will be 0. Is it right? That's what they're telling you right here. Assume Q initially low. You get that?
Yes.
Right, I didn't hear you.
Yes. Assume that Q is initially low.
Okay, now. So basically, okay, I want to know from here to here. What Q?
One. You just look at the truth table. S is 0, R is 1. So S is 0, R is 1, Q is 1.
That's what I try to teach you. If you're looking on the part I already showed you, S equals 0, R equals 1. If you want to know Q, looking into the truth table, S 0, R 1, what Q?
1.
1.
1. You see it right here. S 0, R 1, right? Q equals 1.
Yep.
We don't care, not Q, okay? So, Q equals 1. Okay, then now you go into the next one. That means you get a 1 here. You get a 1 here. What give?
1.
1. How?
No change.
No change.
Perfect. No change.
Okay.
You're looking in here, they say no change. No change means equals 1. Now they still be
1.
1. So you know how to looking into the signal and come up with the output cue, right? You get that?
Yeah, so the next one would be not allowed, right?
Okay, and if you're talking about next one, so you get 1 and 0.
Oh, 1 and 0. Oh, 0.
That's
So it would
one.
be 0. If
0.
if we're including S, then it would be 0.
Perfect.
Okay.
Only thing I try to make sure I bring it up the signal, you know how to using the table to telling what cue. Okay?
Uh-huh.
We're not talking about not cue.
Okay.
The thing is that they from the textbook, they not doing a good job on that one. Okay? Now, that one may be better. You understand a draw cue output waveform for given at a flip-flop. First thing, R1 at 0. What cue?
0.
R1, right? At 0. Q equal 0. Is it correct?
Yes, 0.
Okay. The next one here, 0, 0. What cue?
No change.
Change.
Same thing, no change, right? And the next thing will be 0, 1. R0. Q equal
1.
and 0, 0. Is it correct?
Yes, sir.
Okay. Next one will be 1, 0. S equal 1. Now, S equal 0. R equal 1.
Zero.
That's how output look like. They given you the symbol and you get the table. Okay? So that will be telling you. You understand what guild supposed to be or not guild supposed to be. Any question? Now, next one. They're talking about get at a lot. Okay. This is the symbol. This is the circuitry inside that symbol. Okay. So basically, you know this will be NAND gate. What gate is it here? In order how to understand, easy way to draw that out. And not here. Inverter. If you get A here, B here, at this point, not A, not B, or get output, not A, or not B. That means this is the NOR. Man. Okay, now. If n able equal 0, what in here? This is the NAND. Output will be not A or not B. Enable 0, you get a 1 here. You get a 1 here. Okay? So 1 will be not A, not B. That means output will be 0. Anything will be 0. Okay? However, they only telling you one thing. This circuitry only working if enable equal to 1. Okay? Now, when you're looking into output here, the different bubble here, what that means? If you see the bubble here, what that mean to you?
Low output?
That will be not give. That means not give. Okay. The thing is normally you can say output, they get give and not give. They draw the bubble here, telling you not give. Now, we can try that one. Determine give output waveform if the input cell are applied to the gate at a large initially reset. What that means? Now you need to know a little more. When we say set, okay, that means Q one, okay,
And then reset means Q
Zero.
equals 0.
and reset means 0.
Okay.
Okay, so at the beginning, Q initially reset. If you got draw Q here, I know Q 0. That's only one I know. And now you're looking into enable. Enable equal to 1. So you get S equal 1, R equal 0, S 1, R 0. What gives?
1.
1. Perfect. And next will be enable equal 0. Okay. Enable equal 0. So you still get 1 and 0. Okay. So this will be nothing change until enable equal to 1 again. Then you get a 0 here, 1 here. So add 0, 1, Q 0. Now Q go to 0. And they will be go up to here. The thing is enable 0. Output no change. Okay. Then now enable equal 1 again. And you looking here. C1, 0. Add 1. Q equal 1. And enable 0. So they keep 1 here. Okay. And they can change again. That's only telling you one thing. The table here controlled by enable. Enable equal to 1. Then you're looking into the table to find out what gives. If enable equal 0, Still will be no change. That's it. Okay. That's now they connect into D here. Okay. They call a D latch. Okay. Same thing. Q equal D. Enable equal to 1. If enable equal 0, Q will be no change. Okay. Okay, if you're looking on that one, okay, one thing we know, Q, okay, when enable, okay, otherwise, Q no change. Now I try 1. D equal 1. And also they give it to you here. Q initially 0. So if you could draw Q, I know before I go here, 0. So enable equal to 1. What Q equal? Q equal to D. D1,
Yeah, 1.
Q1. And enable 0, Q no change. Okay. And Q enable equal to 1, Q D0, Q equal 0. See that? Okay. And 0 here. So Q equal to D. Okay. And the 1 here, enable 1 now. So they go 1. 0 now, they equal 0. 1 now, go to 1. That's how signal will be look like. Finally, Q equal to D only enable at logic 1. If enable at logic 0, Q will be no change. Okay, so instead enable, now they using gate. So gate will be controlled. Okay. Problem, draw Q. Output for given D latch. Remember, this is a D latch. First thing, we'll be talking about D. D latch and D flip-flop. Later, D latch. That means D controlled by enable or get here. Okay, that means get equal to 1, then Q equal to D. Okay, get equal 0, Q will be no change. That is a come up with, okay,
And Mr. Pham, can you write that on there?
equal 1. Then Q equal D. Okay, if get then Q no change. No change mean if it was 0, they still be 0. If was 1, then Q still be 1. Okay, now in here, if you're looking on this schematic, you see 2 signals. That one. That one. One they call a preset. Okay. If preset equal 0, Q must be 1. Okay. And if CLR clear, Q must be 0. Okay. And also PR, PER, and CLR cannot zero at the same time. Okay, you understand it in your computer. Everything controlled by the clock signal. So that's why when you buy the computer, they're asking you what frequency you want. High frequency, the computer runs faster, cost more. That means clock keeps running forever. So, for some reason, sometimes we want to set the output Q to be a 1 or to be a 0 without the clock. We can do it. So that's why normally the flip-flop inside the computer, they have to get those two input signal. In case I want to set the output Q to be a 1, I can do it. Clock cannot do anything. I want to set the Q to be 0. We can do it. Okay. If you're looking on the waveform here, you see that is the gate 0, 1. This is clear 0. And that will be 1. And that is D 1 0. Now they want you to draw Q. Who can draw that? Q here. At the beginning, what Q?
0, low.
0.
0. How do we know?
It always starts out 0.
How do you know Q is at the
Gate,
beginning 0? Tell me. The thing is you're doing working easy on the binary. If they're not 0, they have to be 1.
Right.
They're not 1, they have to be 0.
pure 0.
So now you say at the beginning Q equals 0. My question is how you come up with Q equals 0?
Pure 0.
The thing is on the setup, they say nothing. They just say draw Q output for that flip-flop.
Is it just an assumption?
No, cannot assume.
If clear is
No.
0, then Q is 0.
Yeah, you're supposed to assume that Q is initially low.
No, not assume. Not allow you to assume.
Clear CLR is 0.
Who can tell me why at the beginning Q equals 0?
Oh,
Clear is 0. Q is 0.
Perfect. You're looking into here. See? Clear equals 0. They're telling me 0 here at the beginning. I already telling you. Clear 0. Q must be 0.
that's right.
So that's why I draw Q equals 0. Okay?
Mm-hmm.
And the next get equals 0 here. D equals 1. Now, what Q equals?
0.
0. The thing is, get 0 Q will be no change.
Exactly.
Okay?
Mm-hmm.
So now you get D equals 1. And now the get go to 1 here. What Q?
Q equals D. You
Q
draw the
equals D.
exact shape of D,
They go 1. Correct?
right?
Next one. Q equals
Well, the gate is still high.
Right.
So then you draw what D is.
Perfect. That means when the gate at logic 1 Q equal to D, D high, they high. D low, they low. D high, they high. D low, they low. Correct?
Correct. Hey, Mr. Pham, don't that well, never mind. No, never mind.
Up to this point, any question? I said, you guys try to make sure you understand.
So now the gate is low for a while, so then there'll be no changes.
Perfect. No change mean it was 0. Now they have to be
Yeah,
correct.
right.
Okay, now get high again.
Yeah. Q equal D again.
Yeah.
So
High
you draw
equal
D.
D. D 0. Q 0. D 1. Q 1. Very easy. Any question? Flip flop. You can get the time to read it. Flip flop asynchronous bistable device. That means two stable. Also known as bistable multivibrator. In this case, the term synchronous means that the output can state only at a specified point, leading or trailing edge on the triggering input called the clock, which is designated as a control input. So basically, the flip-flop here, same thing like the one we already know. We already know here. Okay? Only thing is, now the gate will be changed by the clock. Okay? And they will be controlled by the clock signal. Okay? The clock signal, they will be positive or negative. Now we see that. At trigger the flip-flop logic simple. Positive X trigger or negative. So you see QD and JK. Okay. Basically, you can see on the D here. Okay. Q equal to D. When C clock zero to 1. Transition. That means Q only equal to D when you get a clock going 0 to 1. Without a clock, Q will be no change. If you understand that one, easy to understand another one. JK flip-flop. You get input J input K and the clock. However, the clock will be negative going. That means the clock going high to low. Now, talking about D first. D equals 0. Q will be equal 0 if you get the clock going 0 to 1. Without that clock, Q cannot be equal D. Same thing, Q equal 1. When you get the clock going 0 to 1, Q equal 1. And another one, JK flip-flop, J0, K0. When the clock going high to 0, output no change. Now you know that what that means, no change. No change, that means it was 0, then now they 0. It was 1, and now they 1. When you get the J0, okay, K1, when you get the clock going negative, Q0, not Q1. And the next one, 1, 0, with the clock Q1, not 0. 1, 1, now toggle. What that mean, toggle?
Go from 1 to 0 or 0 to 1.
Yeah, toggle.
You go to the next state. Hey, Mr. Pham,
Yeah,
is it correct to say in electronics, 0 is a state and 1 is a state? And if you go from 0 to 1, you're going from one state to another state?
yeah, you only either 1 or 0, nothing else.
Okay.
Okay,
But I heard you use the term state before. This state,
that means 1, or that means 0.
okay.
Okay, toggle mean if it was
It was 1, now it's 0. It was 0, now it's 1.
1, then now 0. Or if was 0, then now 1. That means toggle. Okay, now, did I see? Seventy-four. D flip-flop. 14 pieces. You see that pin 1, 14. Normally, on the IC, 14 pins, 14 will be 5 volt, 7 will be ground. Okay? Inside it, I see how many flip-flop?
2.
2.
2. Okay, now you can see. First one here. Second one here. Okay? And they already telling you what pin 1 what pin 2, pin 3, pin 4, whatever. Okay, that's for 74. Okay, now when you see 74, they can be the same. Okay, 54, 74. The difference between 74, 54. 1, 74 for commercial, 54 for military. The same IC. Okay, you can buy for $2. However, 54 cost about $5. The king in military, they get a high quality. Even they just a D flip-flop. And the same thing for you. JK. That are two very, very important for everyone. JK here, you get total pins, 16 pins. However, the power will be pin 5. And the round will be 13. That plus 5 volt. That will be round. That different from normally IC. Normally IC, 16 pin, 16 will be 5 volt. 8 will be round. However, especially for 74, 76, power will be 5 volt. 13 will be round. Inside that IC, you get two JK flip-flop. See, okay, basically, that one they're talking about ports. That means they get a big clock here. They want it to be a small one. See the way they do it. They connect inverter to the NAND gate and inverter. Okay? So when you get this inverter go to the clock here, you go to the inverter. They opposite. Okay? And then another one they still here. They go to the NAND gate. So that's why they opposite. Okay? You get a small one. When you go inverter again, you get the opposite. So only thing is, this will be a big one. This will be a narrow one. Okay? That you don't have to do anything with that. Now, on this D flip-flop, especially not scale, connect to D. Okay? That's only telling you scale, toggle. X time clock zero to one. When they connected not Q into the D, every time you get a clock going 0 to 1, they toggle. That means it was 0, now they go 1. It was 1, now they go 0. That apply the same, okay, for JK when they tie to 1. Okay, we can say same. If J K connect to 1. That will be telling you, if you see JK connect to 1, when you get a clock, output will be toggle. Toggle, it means it was 0, now 1. It was 1, now 0. And this here, they get to the flip-flop. Okay? And basically, you get a QA. And also they draw for you a QB when the clock going 0 to 1. Transition here. Okay? So that they already given you the answer. Frequency division. That only thing is, that will be divided by 2. If you get a 1 kilohertz, then the output coming out here will be 0.5 kilohertz. And the output in here, 0.5 divided by 2 again, 0.25 kilohertz. Okay? What they want? Determine Q and not Q output waveform of flip-flop as shown for the D and the clock input in below timing diagram. Assume that the positive X trigger flip-flop is initially reset. So they gave us the clock. They gave us D. They want to draw the Q. Okay? Only thing, make sure you understand the clock only right here, 0 to 1. Without 0 to 1 transition, there will be no change. Okay, at the beginning, 0. Okay, now telling me when you get a clock, what Q?
One.
Scale equal
D,
1. How come? Again, I try to repeat for you. Scale equal to D when the clock going 0 to 1.
Zero.
So, at the beginning, give 0, okay? When the clock going 0 to 1, what
Q
scale?
Q is equal to 0.
Scale equal 0. The thing is D equal
0.
0. Scale will be equal 0 to the next transition. Okay?
Yes, dear sir.
And the next transition, then what scale?
Same thing.
Still be equal D. Okay? Next transition,
It's high. D is high.
and that will be right.
Okay.
That's how they look like. Any question about this problem? Let's see. JK. Same thing here. Initially, reset. I know at the beginning, they will be okay. And the clock negative going. You see right here. That means the clock will be going 1 to 0. Okay, so that means the clock will be here. 1, 2, 3, 4, 5. Okay, so initially Q 0 up to the clock transition. At the clock transition, you know, want to know Q, you need to know JK. What J equal?
One.
1.
J is 1 and K is 1.
K 1. You look into the table. They say toggle, right?
Mm-hmm.
Toggle mean it was 0, now they go to
1.
1. Okay? And the next clock, J0, K0.
No
They-
change.
No,
No change.
no change. They 1, they still be 1. Okay, next clock, you get 0 here, 1 here. J0, K1.
Output 0.
0. Okay? And now you get a 1, 0.
And go high.
Okay? Going 1, right?
Right. And that last one look like it's high, low. So that would be a 1.
1.
Yeah, right there. That's 1.
basically, not too many, but if you understand it, this is not a problem. That's what engineering worry about that. For digital. Okay, up to here. Any question? Anything? Okay, if it's not, then I will be stopped, okay? And we'll see you guys on Monday.
Okay, thank you. Have a
All right,
nice
thank
Thank
you.
you.
Have a
weekend.
good
Have a good weekend.
Huh. You're welcome.
Bye-bye.
Bye.
Bye-bye.